Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Roberto Rubboli, who will tell us about quantum conditional entropies. And Roberto is a PhD student at the Center for Quantum Technologies in NUS in Singapore. His supervisor is Professor Marco Tomomichel. Previously, he did a master's in physics University of Bologna in Italy. And his main focus is on the mathematical foundations of quantum information and its implications for quantum resource theories. And additionally, he has some interest in exploring various optimization methods that's used in quantum information. Yeah, so Roberto, the floor is yours.
Okay, thank you very much, and thank you for the introduction. Okay, so now today I will talk about my last project on quantum conditional entropies. That is a joint work with Milad Godarzi, that is a postdoc here in our group, in Marco Tomamichel's group, and Marco Tomamichel, who is my PhD advisor. So I want okay, some people might be familiar with this topic, but I will try to motivate our research and give some more introduction on these conditional entropies and in general divergences and towards a complete picture of conditional entropies. Okay, I want to start with classical entropies. So classical entropies are measures of uncertainty, and you might all know the Shannon entropy that has this formula in equation 1. And so we would like to single out what are the properties that a measure of uncertainty should have. And one property is monotonicity under mixing. So basically increasing uncertainty that just increases the measure. So if I denote T as a double stochastic map, then any measure of uncertainty should increase. So for example, the Shannon entropy is one example of such entropy, but here I will denote with this H, which is a bit different, any function that satisfies this property. And eventually I would like to characterize all these functions that satisfy the desired properties. Another property that we would expect is additivity and the tensor product. So this means that if you have two uncorrelated systems, then the uncertainty should just be the sum of the uncertainty of the single systems. And so why we are interested in these two properties? Well, in information theory, you look at quantum information tasks, and these are very natural property to expect for a quantity that would characterize such an information task. For example, Shannon entropy, that is a special case, would just show up in data compression. Okay, so what do we know about entropies? Well, we have a quite well, at least classically, we have a quite well understanding, because basically all the quantities satisfy these two properties are given by the so-called Rényi entropies. And these are just generalization kind of Shannon entropy. So we have a parameter alpha, and the Shannon entropy actually is a special case of that, and is recovered by in the limit alpha equal to 1. Okay, so these are classical entropies. So what about classical conditional entropies? So when you have some side information and you want to measure the uncertainty of, in this case, X, given the knowledge, the side information of Y. So as you might all know, there is an example which is like this conditional Shannon entropy, which is just the weighted sum of the entropy once you fix Y, sorry, and the entropy is just the quantity, the Shannon entropy for a fixed Y. So what about conditional entropies? Well, here the picture, maybe it's a bit unclear, but at least some properties that we would like to satisfy is monotonicity under double stochastic map on X. So if you mix X, you should increase the uncertainty. The other property would be under any map on Y. So basically, it means that you can just process your side information as much as you want, but that won't give you more certainty about the X. And another property is also of additivity under tensor product. So for uncertainty of uncorrelated systems, is sums up. And well, for classical conditional entropy, we know this conditional Shannon entropy, but we don't have a complete understanding of all classical conditional entropy. And actually, later on in the talk, I will show you more new conditional classical entropies that we also recover as a special case of our new quantum conditional entropies. But we still don't have the full picture. And this is because the side information makes the problem non-trivial. Okay, so before going to quantum conditional entropies, I want to discuss a related topic, and it's relative entropies. And so one such example is kind of quite famous. It's called KL divergence. So the KL divergence is a relative entropy and has this form as in equation 11. And it satisfies two properties. One is the data processing inequality. In classically means it's monotone under stochastic map. So the relative entropies are a measure of distinguishability, so between the two states. So basically, so they are zero when the two states are the same, and non-zero when they are not. And what we would expect is actually this this data processing inequality, so monotonicity under maps, which means basically that if you add noise, then you shouldn't increase the distinguishability of the two states, or in this case, probability distributions, because they are classical. And another property we would expect is additivity under tensor product. So for uncorrelated states on both, so P tensor R and Q tensor S, then the divergence should sum up. So the distinguishability should sum up. And also these divergences, they show up in some operational tasks. And indeed, these two are very natural properties to require for a function that characterizes your information task. So we would like, so do we have understanding of divergences? Well, the answer is yes, meaning that classically, they are basically given by the Rényi divergences. So you can see the formula in equation 14, which are characterized by a parameter alpha. And if you go alpha equal to 1, well, you will recover the KL divergence. So, okay, why do I need to talk about divergences? Well, because you can build out of a divergence an entropy and then a conditional entropy. So a Rényi entropy, you just input your probability distribution, and then you on the first argument, on the second argument, you just set the fully mixed state. While for conditional entropies, you would just take your joint probability distribution X and Y, and on the second argument, for example, you can take the identity tensor PY. PY is the margin of PXY on Y. And you can check that from the properties of the divergence, these are proper conditional entropies. So basically, the conditional entropy built in this way inherit the nice properties from the divergence, and they satisfy the property we like for a conditional entropy. And this is a way to construct conditional entropy in equation 16, but it's not clear even classically whether all classical conditional entropies could be written in this form. And so this is what we are going to do, basically. We will, in quantum, you can usually define conditional entropies out of divergences, as in equation 16, using quantum states. But this is not the full picture classically, so it won't be even the full picture quantumly. But I will come up to this point later. So, okay, quantum relative entropies, well, in this case, they are the measure of distinguishability between states. And one example is the Umegaki relative entropy in equation 17 that generalize the KL divergence. And two properties that it satisfies are monotonicity under quantum channel, which generalizes the monotonicity under stochastic maps for the classical case, and additivity under tensor product. But we don't have a full picture of quantum relative entropies. So we know some quantum relative entropies, but we don't have a full understanding. So we also don't have a full understanding on quantum conditional entropies, since you can build the quantum conditional entropies out of quantum relative entropy. So, okay, for quantum conditional entropies, well, the properties are even a bit more debated, but for example, you can look at the von Neumann conditional entropy, which is built using the Umegaki relative entropy in the way I just discussed before. So you just set on the second argument that this identity tensor the marginal of the state. And then you would ask, what are the properties we would like a conditional entropy to satisfy? Well, at least some properties are the following. So it should be monotone under any channel acting on the side information. And it should be monotone under unital channel acting on the primary system. So in this case, A. And it should be additive on the tensor product. So I didn't explicitly write what this means, but you can easily understand from what I wrote from the classical case. And well, maybe some more properties could be required, and this is a bit debatable, but at least we think that these are kind of a fundamental properties for a quantum conditional entropy. And yes, of course, the question is, do we understand them? Well, we don't understand them even classically. We don't understand quantum divergence. We can build conditional entropies out of divergences. So of course, we don't understand quantum conditional entropies. But in this talk, I will show you some steps towards some bigger understanding of this problem. Okay, so one might ask, do we need all entropies? Well, people often ask me, why would you even look at conditional entropies that are not just the conditional von Neumann entropy? And well, for some people that are in the field, it's kind of clear. And but I will just show you a few slides. I hope to motivate you why you need several conditional entropies, these alpha generalizations, and hopefully also our new conditional entropies that I will talk later. Okay, so the first I want to talk about hypothesis testing just briefly to motivate. And here you would like to distinguish between a state rho tensor n or a sigma state tensor n. And what you do, you just perform a test, and based on the outcome, you would say that either is rho or sigma. You don't know, so you don't know which state is given, but you would like to find it out. And you can make two errors. So one is when this alpha n, and the other one is this beta n, is when you say it's sigma, it's actually rho, and vice versa. It's rho, but you say that it's rho, but it's actually sigma. And the goal in hypothesis testing is to minimize these two errors. And then there are these results. So the first is called a Stein exponent. So when you increase the number of copies n, you can distinguish better and better rho and sigma because they get orthogonal. And the success probability is going zero exponentially, and the Umegaki relative entropy gives the rate of this decaying. But so someone could say, okay, then we just need the Umegaki relative entropy, but this is not quite the case, because if you look at the decaying of the sum of the sum of the two errors, then you would get this maximization. So with this d bar alpha, and this is the Petz relative entropy. And this is I will talk later about Petz relative entropies, but this shows that somehow there is no one. To me, at least, it sounds like we actually might need all of them, and we should have a clear picture which task should single out some quantities rather than the other. And especially if you have a unified picture, you would have I think a thorough understanding of what quantities should appear. Okay, so I hope I'm motivated, at least the alpha parameter. So here we have d and the alpha, and this is for divergences, but for relative entropies is connected. Now I will hopefully you will accept two more parameters, z and lambda. Okay, so let's turn to the zoo of quantum conditional entropies. So in the literature, usually these are the conditional entropies that are defined, and they are defined through the sandwich Rényi relative entropy and the Petz relative entropy. And they are either, so there are this tilde denote the sandwiched, whereas the bar denotes the sandwich, the Petz, and the arrow up, it tells you that you optimize over all states sigma b, whereas arrow down tells you that you just input the marginals rho b. And then you could do the same for sandwich and Petz, and you could define at least four quantities, 4 conditional entropies. And this is kind of messy because are they all the same quantity? It's like it's a bit unclear how one would look at them and which one to choose. And in the literature, there were these existing following duality relations. So okay, here I didn't state it, but here rho you consider a pure state rho ABC. So for a pure state rho ABC, the entropy of A given B plus the entropy of A given C equals to 0. And the parameter change as to satisfy some specific relation. So for example, for sandwich arrow up, alpha and alpha hat, they need to be connected by this relation 1 over alpha plus 1 over alpha hat equal to 2. For then there is this relation for Petz arrow down, where alpha plus alpha hat needs to be equal to 2, and finally a relation that connects sandwiched arrow down and Petz arrow up. And this seems, I mean, all these dualities, they had different proofs. So it was not, so the last relation especially suggests that there is a connection between sandwiched and Petz. But, this hints to a deeper structure that should kind of involve the same entropy, same conditional entropy. And indeed, this was kind of our starting point. And the main question was, are all these duality relations just one duality relation of, and do they come from the same quantity? And actually the answer is yes. And this is the main result of our work, a new conditional entropy. So this is the new conditional entropy. So it tests 3 parameters, alpha, z, and lambda. So the z parameter is, so the alpha parameter is the classical parameter, meaning that if you just evaluate for classical states, then you would have like a classical Rényi conditional entropy dependent on alpha. The z is kind of the quantum parameter, and you can think of it as distinguishing between Petz and sandwiched. And finally, there is another parameter lambda that is also a classical parameter and tells you whether you optimize or non-optimized. Okay, so a bit more in depth. So let's start from lambda. So inside the formula, you can see that rho b and sigma b, they are to the power 1 minus lambda and lambda multiplied by other constants. But especially when lambda equals to 0, then the term on sigma b gives the identity, and you are left with rho b. So you get the arrow down. Whereas when lambda is equal to 1, you are left only with sigma b, and you get the arrow up. Here I use this symbol opt to denote an optimization, which might be either a sup or an inf, depending on the values of the parameters, basically depending on whether the function is concave or convex. And so for alpha equal to 1, one can actually see that one recovers the von Neumann conditional entropy. Well, not always, but because you actually recover in some specific limit some exponentiated mean of the conditional entropy, but that's some caveat. So basically, in almost all the cases, you recover the von Neumann conditional entropies. Whereas for lambda equal to 0 and lambda equal to 1, you get the arrow down and the arrow up. So if you go farther down, for z equal to alpha, you will recover the sandwiched conditional entropies, whereas for z equal to 1, you recover the Petz. And for general alpha z, you actually recover some kind of exotic Rényi conditional entropies that you can build out of the so-called alpha z Rényi divergences. So that's why we use this name, so alpha and z. And for alpha equal to infinity, well, you recover what would be the minimal. So means like the smallest of all these conditional entropy. Meaning that for just any state, this quantity will give you a number that is smaller than what all the other quantities would give you. And whereas for the sandwich arrow up, for alpha equal to infinity, alpha equal to 1/2, you recover the so-called mean and max entropy, which have special roles in QKD, and so they have their own name. And whereas for alpha equal to 0 in the Petz case, you would recover the maximal conditional entropy. Okay, so here's the duality relation, and this is our first result after introducing the new conditional entropy, is that this duality relation between alpha z and lambda and alpha hat, z hat, and lambda hat. And this, you can check that this unique duality relation for special values of the parameters, we recover all the three duality relations, maybe here, that I discussed before. And yes, and then you can see this three equation. For example, you can fix alpha, z, and lambda, then you can solve for alpha hat, z hat, and lambda hat, because you can have three equations with three parameters with three equations. So basically fixing the primal, this h alpha z lambda a given b, you will uniquely determine the dual values, the values of the dual parameters alpha hat, z hat, and lambda hat. And this is kind of nice because it tells you that there is this hidden structure, and all the relations are coming from here. And it would be interesting to investigate how the specific case come up from these underlying structures in applications. Okay, so then we looked at data processing region. So what values of alpha, z, and lambda we can take such that the conditional entropy satisfy the data processing inequality, meaning that I can act with a unital channel or actually subunital on the primary system A, or I can act with any channel on B. And this is the range we found for the parameters, which is quite complicated. And actually, we find that also lambda parameters negative can be. So before people were looking at arrow up and arrow down, which are for lambda equal to 0 and lambda equal to 1. So we find that we can interpolate between these two values, but we can also extrapolate. So we can also have negative values of lambda. And yes, so the proof here is quite technical, but you can check the paper. And okay, and our last results is about chain rules. So there was this chain rule for sandwich Rényi entropies that you can it was by Hui. So basically, once we understand that we have a unique structure, one can hunt the archive. So look in the archive for properties that have been proved for example, for sandwiched, and just prove it for Petz, for example. Once you realize that they share a common structure, and this is what we did. This is in some sense one application, even though it's kind of on the mathematical side of our results, is that once we realize that they are all the same quantities, well, one can just hopefully use the proof of a specific case to prove the whole case, and this is what we did. So this is the chain rule we get. So it's we get if for example all parameters are bigger than 1, then this product here is positive, and then we get that the entropy of ABC is given C is bigger than A given BC plus entropy of B given C, with some rescaling of the with some relation among the parameters. So, and the parameters, they have to satisfy this relation number 37, which is kind of elegant. And maybe here I just write down some special case because, okay, it's a bit abstract, but so the known ones were for sandwiched, but here we put the one for Petz. So and some mixed ones between Petz and sandwich, and our special cases of the unique duality relation I just stated before. For example, the first two involve the Petz arrow up and Petz arrow down, whereas the other one, they involve some mixed chain rules between Petz and sandwiched, and these were not known, and somehow, yeah, well, one could have found them by just looking at specific case, but here it's quite nice that we just have one chain rule for everything, and it's kind of nice. Okay, so other properties here, maybe I will be a bit faster. So of course, yeah, like one main property is the additivity properties, right? So here we prove that these quantities are additive, and then we also prove monotonicity in the parameters, meaning that it's increasing in alpha and increasing or decreasing in z depending on some ranges, and also increasing in lambda. And actually this proof, especially the monotonicity in lambda, they are quite involved, but eventually we made it. Okay, and so here we have some clear relations between two values of the parameters because of these monotonicities. Okay, last thing I wanted to say is classical conditional entropies. So as I discussed before, we don't have a clear picture of classical conditional entropies, but if you look at diagonal states, then for our new conditional entropies, then we obtain also a new classical entropy. And here we use this, you can see the formula in equation 46, where beta is defined as a function of alpha and lambda. So basically z disappears, and then we are left with lambda and alpha, and then we just redefine this variable beta just for compactness. and then one can just specialize the DPI regions we found for the quantum case, and you can see that it has to be that either alpha and beta are between 0 and 1, or they are both bigger than 1. And one can specialize also the chain rules, and one can find some new chain rules. For example, here I listed for the classical cases that have been studied. For example, the A stands for Arimoto, which corresponds to the optimized case in the classical case, whereas H here denotes the Hayashi. It corresponds to the non-optimized case. So basically, lambda equal to 1 and lambda equal to 0 that turn into a beta equal to 1 and beta equal to alpha. And this is, well, we don't know if there are any nice application for this, but at least classically was not known, and actually classically some of the chain rules are also not trivial, and so our methods, our quantum methods actually can tell something about classical chain rules. Okay, so I would be finished if you. If you have some questions.
All right. Yeah.
Or maybe I can still keep it.
Yes, probably can still keep it. Just.
Yes,
yeah,
I was faster
to the slides.
I was faster than expected.
Yeah, I suppose that's not usually a problem.
But
Yeah,
Friday,
yeah.
it's a Friday, so I guess it's appreciated.
Yeah, true. Right, yeah. So yeah, if anyone has questions, please feel free to just unmute yourself and ask now.
Okay, maybe I can talk. Yes, I can say about some further direction just briefly. So one direction we have is that, okay, we have these nice new conditional entropies, but can we give them an operational meaning that can we find a setting where these quantities show up? And well, we didn't have time to look at this, but maybe in some hypothesis testing or betting games or some other scenarios where actually the special cases show up, we can find some interpretation for also for these conditional entropies that interpolate between the known interpretation. Yes, and maybe that's the one open question that we still have. And yes, so this quite recent, this work, so we haven't had many developments after this, but okay, you can ask me a question if you wish.
All right, Hector. Yeah.
So in a similar vein to the question you answered earlier, can you, I mean, some of the entropies you talked about, you were saying that it is known that this is the set of all entropies up to convex combination. And then for others, it wasn't known. Can you kind of maybe motivate why you would care that you know the set of all entropies?
Yes. So okay. So one, it's quite well, it's arguable, but if you know all of them, then you would just have the proof, like all the proofs. Okay, this is a theoretical reason, but all the proofs, they would just be for one quantity, and you would not need all the specialized proofs. But this maybe is not so convincing. The other one is that if you know all of them, and then you have some task, and you expect that some of at least one of them will appear, then you would know what at least the form that you expect it to appear. And the other final reason is that there are some tasks that you actually need all of them. And for example, I've been working on asymptotic transformation or catalytic transformations, and there are some tasks, for example, in catalysis that you would need, for example, in LOCC, catalytic LOCC between pure states, if you want to transform one into the other, then you would have to consider all of them. And if you look at rates, all of them appear. So there are some tasks where you actually, if you have a clear understanding of all the conditional entropies, then you would completely characterize your task.
Okay, and can I thank you for that answer. Can I just have a follow-up? Did your generalization in the quantum setting shed any light on this question about the set of all entropies, either in the classical setting or in the quantum setting?
Yes, so in the classical setting, we find new conditional entropies, but we don't solve the full picture. In the quantum case, we find new conditional entropy, quantum conditional entropies, but we don't solve the full picture. But this is some kind of Rome was not built in one day, maybe some people would say. So we hope that at least now we have a better understanding of all the static quantities that have non-operational interpretation. So yes, the question whether one day we will ever be able to solve the full problem, or how far is the full solution to this new conditional entropy we find, it's a bit unclear.
Okay, thank you.
You're welcome.
Right. So do we have other people? Maybe I can briefly ask something.
Okay.
So yeah, like I think you mentioned something about, so for this lambda parameter, so it reduces the things that we know when you are like within 0 and 1, but actually you can extrapolate, right? So I suppose lambda actually allows, is that like any real number is allowed?
So here is the here's the DPI region, see in 35. So lambda is between 1, for example, for alpha is more than 1. Lambda is between 1 and 1 minus z over 1 minus alpha. So on the left hand side, this 1 minus z over 1 minus alpha is generally negative, but it goes to minus infinity only when alpha is going to 1. So in general, it cannot be any real parameter between minus infinity and 1. But in the limit alpha equal to 1, yes, it can be any parameter between minus infinity and 1. And also in the limit z equal to infinity, it can be between minus infinity and 1. And actually, this lambda equal to minus infinity brings a new conditional entropy, which is if you approach lambda equal to 1 and at the same time you approach lambda equal to minus infinity, you won't recover the usual von Neumann conditional entropy, but you would recover a new, an exponentiated mean of the for the conditional entropy. So for you just average with py in an exponential sense the hx of y given a specific value of y. So yeah, I haven't put it here, but I think we mentioned in the paper in the conclusion. So in the conclusion, we mentioned this quantity for lambda equal to minus infinity. So yes, sometimes lambda can go to minus infinity and can give you some strange quantities.
Jakob, yeah, sure, go ahead.
Yeah, so one more question. I don't know what exactly the answer to this would look like, but do you have any comments about how hard it is to compute these entropies for a general state that's not, you know?
Yes, so usually people don't care about at least in quantum information computing these entropies, but there are some people that care about, and so okay, how hard? So practically, so for some entropies, like for some values of the parameters, we have STPs, for example, and well, in general, it's a convex optimization. So in principle, you can compute it with just gradient descents, but that might not be fast in the sense that if you have a 4 qubit, you might need to actually wait for hours or days. So actually, I think I had a project on evaluating a special case, which is this max conditional entropy, and I believe yeah, my one of the authors also talked at this in these talks in Foxconn. So we had this project on evaluating the max conditional entropy using a fixed point algorithm that is also can be interpreted as a Riemannian gradient descent, with unit step size, which seems to be very efficient, and it kind of has very good performances with respect to the STPs. So here I'm advertising my other work. But yes, like finding efficient algorithms to evaluate these quantities beyond just few qubits, it's a very active topic of research, and there are many ways you could do.
Thank you.
Yes.
Yeah. So yeah, is there anyone else with questions? I sort of like, okay, maybe it's kind of naive question. Like, so do we know that this has to be sort of like the most general way to characterize the conditional entropies? Like, or would you imagine that maybe there's still some hidden parameters that are
Yes,
sort of
no,
like
we
fixed
know
from this family?
we know that this is not the full picture, not even classically. So for example, if you look at the classical case of these conditional entropies, they won't give the full picture. So meaning that in the literature there are some classical conditional entropies that cannot be recovered as our.
Okay.
So even quantumly, one could define other quantum conditional entropies. So for example, one could use like the geometric Rényi divergence that is not captured by this definition. Anyway, yes. So either I believe that there could be more parameters, and eventually there might be just one way to just write down one quantum conditional entropy. That's one case. But anyway, at least our definition just captures the most used, and at least all the ones that have operational interpretation. Since the geometric, the one based on the geometric Rényi divergence, to the best of my knowledge, they don't have any operational interpretations. Whereas the one we capture here are widely used in many contexts and have many operational interpretations.
Is there are there any, like, have you guys considered additional constraints that you might put on an entropy that might make the picture a bit simpler or nicer? That would be like a natural property in addition to the two you're already incorporating?
Not really. But yes, we don't expect. We don't. Do you have any properties in mind, or?
No, I mean, I guess maybe you have three, right? Because you have like the
Yes.
data processing inequality in addition to
Yes.
the additivity and the
Yes.
monotonicity. Yeah.
Yes.
Yeah, I guess like in some sense what you're saying is like you will try to add more properties to this list But I suppose maybe in a mathematical sense they would be less natural, but maybe they will be natural in a different sense.
Yeah, so okay, so there is this paper here, number 11. This Gur Wilde Branston, Brunson. They look at other. They look at very general class of properties that include these ones. So yes, it's a bit. So it hasn't been explored much. What actually are the properties that quantum conditional entropy should satisfy, and or maybe some restricted settings. But yes, so at least this paper goes in this sense, and yes, we haven't thought much how to add more properties, because at least these ones are the one that look natural, whereas some additional properties, I mean, it's a bit debatable, and okay, also one maybe might consider a specific task, and yeah, that might be a good direction to get something, but at least these three properties are really like kind of what we believe we should have.
Yeah, I mean, I can imagine like in some sense like the problem is intertwined, right? If you have a better operational understanding of this quantity, then it would sort of maybe reveal to you what is a natural property that these quantities have, and sort of like I guess sometimes you have to solve one or the other first, and maybe maybe that helps. I don't know. Yeah, just speculating.
Yes, yeah. That's a good direction, I think. But yeah, I don't know how easy it's gonna be.
So are these sorry, this is a very naive question, but are these all these properties closed on the convex combination? I mean, additivity doesn't seem like something that's maintained.
So you take convex combination of rho of so okay, I haven't. So additivity means that you have okay, I wrote it down in the classical case. Yes, so in this last case, equation 9. So you would mix yeah, like where would you take convex combination on P or Q?
I meant, so I guess I meant like, yeah, I guess it's a bit more complicated with the conditional entropies. I guess you might keep y constant and take a convex combination of x's.
But you have correlations between y and x. So you just mix between joint distribution with the same marginal on y.
Yeah, I'm not sure. So when you talk about convex combinations, what did you mean?
I mean,
like I thought you were talking about defining entropies from convex combinations of other entropies.
Yes.
Is that not what you meant?
Yes, that's what I meant. Like when I were discussing before,
Yeah.
like this one, up to linear combinations.
Yes.
Yeah. So yes. So if you sum them, yeah, it's kind of clear that, for example, here, if you sum two of them with some coefficient lambda and 1 minus lambda, then also the convex combination is additive, because you get lambda multiplied by the sum plus 1 minus lambda multiplied by the sum, and then you can just group the first entropies on and then the second ones. So if you take the sum of two, if you take the sum of two, then it's gonna be also additive, and it's also gonna be monotone because each of the term in the sum is increasing. So yes, so just taking just summing two of them, at least in these properties, will always give you a new conditional entropy. But we are kind of interested when we look at these problems. We are interested in the extreme points. So yes, we can always take convex combination, but we are looking at a like a
basis for the.
Yes, like a basis. Yeah, exactly. You can always, basically you can always sum two of them and get a new one. But this is not telling you much. We are just interested in the extreme points, basically, when we write these conditional entropies.